Thanks very much. To explain the name, it's actually pronounced CausaLens. CausaLens. And I'll tell you in a little bit why we named the company like that. So we are in the field of trying to understand time series data. And so as a first step, I'm going to tell you a little bit about what time series are. And really, time series are just measurements of some variable over some time, right? So in effect, anything that you measure has a timestamp associated with it, right? It's the time when you measured it, right? Unless you're in a physics experiment or a chemistry experiment and you control all the little things, you will always have some measure of a circumstance in which you took some data point and the time when you took it, right? So in effect, everything is a time series, and the time series data is exploding. You've got everything from health data to location data to data inside data centers, measures of load and log and security. You've got obviously financial data, which has been using and collecting time series for a very long time, economics as well, and of course the IoT, Internet of Things. All of these things are generating loads of data, and the world is only becoming more and more driven by all these time series that are being generated. And so that's what time series are. They are numbers associated with time, or they could be categories associated with time. You could say, is it sunny, is it cloudy, is it rainy? Okay, so now we deal with some of the most challenging time series problems in the world. Here is how a time series problem looks like. The green bold time series there is a time series that we are interested in. That could be a measure that we would like to predict in the future, and we want to build a model to predict it, and maybe we have some input variables. Those are the blue and the red here. Those are the variables that we want to use to make this prediction, right? So what is an example of something like this? What would we like to predict? We would be interested in predicting, let's say, a stock price in the future, because we might be interested to make a trade and to buy that stock and profit from that. Or we might be interested in, maybe we are selling some sort of a service and we want to predict what will be the demand for this service in the future. And what we know, for example, as an input variable, is how much money we're spending on marketing, right? So then the question becomes, can I use my marketing spend to help predict the demand or the sales that I'll be making? So the reason I'm calling these problems challenging is because they have a lot of properties that make them really hard. First one is that they're relatively small data. It's hard to collect loads of time series data. And some of the most interesting time series data sets that we have historically are really, really small in quantity. Some of the most interesting macroeconomic data comes out quarterly or even annually. So the data is small. Moreover, it's non-stationary. Non-stationary basically means that the models that these time series, the behavior of these time series is changing over time. It's non-stationary. It's essentially dynamic, right? So, if we build a model today and we put it in production, 6 months from today, it might not work anymore, because in this world, we would say basically the world has changed. The model has stayed the same, but the world underneath it has changed. And so now this time series is behaving in a different way. That's what it means to be non-stationary. The data is also very noisy, because these measures come from all sorts of sources that could be noisy. We use this parlance of sort of time series literature where we call about signal. We talk about signal. So these data have very small signal. In effect, the noise is just high enough that to be able to predict something, it's very hard, because the signal in the inputs is very low. And there's a few reasons for that, and we can go into them in more detail. So how would you go about solving this problem? Where do you even begin? There's actually a number of things you could do. You could go back to econometrics in economics literature, going back to the 30s. You could look at what people in the signals processing world have been doing. Physicists have been interested in this problem for a very long time. And obviously, you can also apply machine learning to it. So what would the machine learning model look like? To first order, it's not that hard to set it up. You essentially, let's look at the bold green time series in the middle. You want to predict it in the future. So that's the two little circles. That represents a point in the future. That's the dotted line represents some point in time. So some point before that, you've got a measurement. You only know what's happening on the left side of that line, right? But what you're interested in is predicting what's going to, where is the green line going to be at that double circle point. So one way to do that would be to just take those 3 points that I labeled with circles and let's say make some sort of a regression of those 3 variables against the fourth one. And then you would have some sort of a sliding window where you would go across this and you would build up a sort of a regression problem to solve that. And if you try doing that, you will find that it doesn't perform very well. It doesn't perform very well for a couple of reasons. It doesn't actually extract all the information from these time series. And quite often it won't work at all because maybe the values in these time series are not what is actually driving this variable in the future. Maybe it is some measure that is somehow associated to the values. For example, the momentum of these time series. So maybe what is driving, so let's take an example. What's driving our sales, maybe it's not the amount that we spend on marketing, but how we are, what is the momentum that we have in increasing our marketing spend, for example. Or maybe the stock price is actually driven by the change in sentiment, in Twitter sentiment, and not in the absolute value of what the Twitter sentiment is today. So that's one example for why this kind of a regression problem wouldn't work very well. And we provide a solution for this. And the way we do it is hard, but it's doable. And there is no single individual technique that just solves it out of the box. So we don't come with deep learning and we just say, here we throw it into a deep learning network and we get a solution. We don't go back to econometrics because that doesn't perform as well either. Essentially, we built a way to optimize across all the parameter space and all the techniques and technologies out there and build an optimal solution by connecting pieces of the models together automatically so that what we end up with is what we call an optimal model, because really it's a model that's extracting all the possible signals from the input variables. That's the idea. So we do that in a couple of ways. We expose a way for humans to interact with the machine in the process. So we give essentially a way for a human to put a prior and to say, I believe that these variables should drive this model. So it's a way for a human to nicely interact with the machine. We figure out how to impute and align the data in the time series world. We extract all these time series components that I talked about, things like momentum, how are the time series changing. There's a lot more of those as well. We select which of those features actually matter. We select the algorithms, the hyperparameters, and we optimize the whole thing. I'll show you a few plots just to kind of get you an idea that does work. When we did this analysis, we applied it to a number of data sets and metrics, and we tried to vary one step in that pipeline at a time. And so one covariate at a time, we try to see, does it help or not, right? So for example, this is the process of letting a human put a sort of a prior on features in the model. And if you measure it as a function of the score, or as a function of the absolute error, or as a function of Pearson R, or some variable like that, you will find that in general, with various different data sets, this process helps and is actually improving the model. If you do feature extraction, or if you don't do feature extraction, you can compare those two and you can find that, well, actually, feature extraction helps a lot. The same is with feature set selection. So, in effect, I showed you 3 of those examples. Those are just some basic experiments that we did where we saw that each of those components helps build better models. But how do we put it all together? That's one question. And in fact, this is really interesting. The sort of classic way a physicist or a machine learning person would approach this is through some sort of a derivative-free optimization. Why is it a derivative-free optimization? It's derivative-free because you're in this really weird hyperparameter space where you are actually optimizing across model architectures, right? So if you think about it, what would it mean to have a derivative, some kind of a difference between a lasso and model and a gradient boosted tree, right? That doesn't make a lot of sense, right? So this is why you're actually kind of in this space that is sort of a Cartesian sum of multiple spaces, and so you can't really have any reasonable notion of derivative. So what you do is you use something that's derivative free, and some examples of algorithms like that are genetic algorithms that you could use. You could do Bayesian optimization as well, or things of that sort. So that's how to first order, that's how we solve the problem. And when you do that, you also see if you do a kind of a full pipeline optimization, you outperform just optimizing each piece of the pipeline. So you could optimize each piece of the pipeline individually, but you could then do, or you could do the holistic thing. If you do the whole thing together, you get more performance as well. So there's quite a few steps, and at the end of this whole process, you built a model pretty much automatically, and that model is close to the best you could do. And now, so what we built is this machine that can generate automatically these models that automatically extract signal from the input data and produce a prediction on the time series. Now that we have that, I think this is a really powerful abstraction. And with the right set of data and right organization, you can now start having these models. You can start building these predictive models internally within your organization. You can kind of start producing these models that are predicting the world, and you can start connecting them together. And in this way, you are sort of building a model of the world. You're understanding the world by using these little bricks that you're connecting, and these bricks are the technology that I just showed you. What is nice about it is that you've got the technology to extract all the signal from the data. So what you then focus on is, well, what data should actually flow in, and how do I model the world? And that's actually the really exciting question as a data scientist. It's not about the nitty-gritty and the derivative-free optimization, right? What's really exciting is, trying to understand and build a model for the whole world. And of course, there is a question that one would like to answer by building this sort of a world. The reason why I have a grail there is because it's a very hard question. It's a kind of a holy grail. It's about understanding what is the reason that things happen in the world, and what causes, what is a cause and what is an effect. The way to do it is if you have a predictive model that predicts something, there's this notion of Granger causality. The idea is if something predicts something else, that means that in some sense, it causes it, right? So it is a sort of a proxy for causation. And that's the reason we named the company CausaLens. I do want to mention very briefly about AutoML. We actually heard from Google today about it, so that's really great. We also, so I mentioned that we apply derivative-free optimization. This is about AlphaGo 0. we also do a sort of an AutoML type of approach to go beyond derivative-free optimization. And so the idea there is that you should be able to build a machine that can be smarter than a derivative-free optimization, okay? A derivative-free optimization, in effect, or let's say Bayesian optimization, in effect, it doesn't have the ability to perform actions on the problems that it's trying to optimize, right? It basically has parameters it's able to tune, and that's all it can do. We've set up this approach where we've got our machine interacting with the true model. We can actually generate data, artificial data, kind of like how AlphaGo Zero plays games against itself. We can generate, let's say, fake economic data that has some sort of underlying economic model that we know, but we don't tell the machine what that model is. The machine can perform these experiments, and it can learn how to build a proposed model, the best model it can possibly build. And then we can obviously score that because we know what the real model is. The machine doesn't, but we can see how well the machine, what experiments did the machine take to figure out that model, and how good was the end result. And we limit the computational budget of that machine because we obviously want to figure out that answer in a finite amount of time. And so this is how we end up setting up a game, in effect, that can solve this problem. And this approach actually does outperform the sort of naive Bayesian optimization you could also do. There's other stuff as well that you can do using this technology. You can look at huge cross sections of data, doing also, looking at thousands of time series at the same time and understanding how they all behave together. It's a very interesting problem also of integrating data at different frequencies, and obviously how do you apply deep learning to time series, and how do you express time series models in tensors. And we can talk about that as well. Please feel free to come and ask any questions. So what I just showed you is how we built one of these bricks, one of these little components in this system. But really what we are excited about is the ability to start using these bricks to build up a model of the world, right? If the only way to do that process effectively is by building an abstraction layer, right? Something that lets you build these bricks and connect them. These boxes, you need to be sure that they are correct and that they are actually extremely scalable. I didn't mention anything about it, but the boxes that we end up building are very transparent. They actually explain to you everything that they are doing, and they're trying the system is trying to build these models in a very human way. And this is very important. If you're trying to model something in the real world, you really want it to be something that's reasonable and that you can understand. Otherwise, people won't believe you, or there is a really serious danger of overfitting, right? And building a model that's too complex and doesn't generalize very well. So I can just very briefly show you a little demo of the technology. So I'll just click here. And it's kind of very similar to the demo that Google has shown as well. Once you have a data set of time series, and once you enter it into the platform, you get what looks essentially just like a usual experiment that a data scientist would set up. So it involves a period where you're training your models, the history, a period where you're validating them, and then what you get is testing as well. And this is just a small UI we've built. But basically, with one click of a button, you can build a model that actually just is as parsimonious as possible. And I'll show you how one of those models looks like. It's a very basic one, but if we click on an old one, because I don't want to wait for it. Yeah, so you can actually zoom in and kind of get the idea for how well this model is performing out of sample, and you can see it point by point. And then you can actually dig through all the little details of what went into that model, how important were the features, what were the responses of the features, and so on and so forth. So, you know, you can evaluate all the performance metrics of that. And in this way, what you've got is essentially a framework to build on top of which to build a whole network of models. So we're based in London. We are relatively early stage and you know, an exciting place to work. We are hiring at least 2 data scientists in the near right now. So please feel free to talk to me about that as well. Any questions?